Good morning, I am Yash Ahuja.
And I am Priyanshu Parakhiya.
We are from Engineering Physics 3rd year, and today we will be demonstrating our practical speed measurement using optocoupler.
For this experiment, we are going to focus on the following keynotes. The first one is what is optocoupler and the basics of optocoupler. The second one is the experimental setup which we are going to use to conduct the experiment of speed measurement using the optocoupler instrument. The third one is how to take measurements and the two different methodologies to conduct this experiment, followed by the calculations and observations which are needed to practically extract the results from the measurements. And the fifth one is the conclusion and what we could gather from the data that we obtained. So moving on. So you will be getting the question like what is optocoupler? So here we will discuss the mechanism of optocoupler. One of the primary functions of an optocoupler is to provide electrical isolation between two circuits. This isolation is achieved by using light to transmit signals across a small gap, typically between an output and an input side of the device. This prevents any direct electrical connection between the input and output, protecting sensitive components or circuits from high voltages or noise. Optocoupler is also known as opto-isolator. An optocoupler consists of two main components, a light emitting diode on the input side and photosensitive semiconductor device such as a phototransistor or photodiode on the output side. When current flows through the LED, it emits light which then activates the photosensitive component, allowing the transfer of signals. When an electrical signal is applied to the input side of the optocoupler, the LED is either turned on or off depending on the signal. The emitted light is then detected by the photosensitive component on the output side, which generates a corresponding electrical signal. This allows the input signal to be replicated on the output side of the optocoupler while maintaining electrical isolation. So what are the different types of optocouplers? There are different types of optocouplers available, including phototransistor optocouplers, which use phototransistors as an output device, providing amplification and higher switching speeds. Then there is photo-Darlington optocouplers, which are similar to phototransistors, but use a photo-Darlington pair for even higher sensitivity and amplification. Then the third one is the photovoltaic optocouplers, which instead of a phototransistor use a photovoltaic cell to generate an output voltage proportional to the light intensity. And now coming on to the advantages and applications. So basically it provides electrical isolation which protects the circuit from high voltages, noises and interference. It also comes in compact size. So optocouplers are typically very small in size, making them suitable for integration into compact electronic devices. And the third one is high reliability, as they have no moving parts and are not susceptible to mechanical wear and tear, resulting in high reliability and long service life. But there are also some disadvantages to this optocoupler instrument. The first one is limited bandwidth. Optocouplers may have limited bandwidth compared to direct electrical connections, which can be a limitation in high frequency applications. The second one is temperature sensitivity. Performance may vary with temperature, particularly for optocouplers using light emitting diodes. And the third one is cost. Optocouplers can be more expensive than alternative isolation methods, particularly for high performance or specialized types. Now moving on to the experimental setup for this experiment. Now we will be discussing about the experimental setup and the components required to conduct this experiment. So the first component required is the optocoupler. It is a photoelectric sensor that detects changes in light intensity as mentioned before. It consists of an LED emitter and a photodetector, and in this setup the optocoupler is attached to a platform alongside a slotted disc. Then we have a DC motor which is utilized to drive the motion of the slotted disc. When powered, the motor converts electrical energy into mechanical energy, causing the disc to rotate. Then we have the slotted disc, which is circular in nature and features 15 evenly spaced teeth around its circumference. As the disc rotates, the teeth obstruct the light path between the LED emitter and photodetector of the optocoupler. Then we have the trainer kit, which consists of a multiplier, wave shaper, as well as the electronic counter with 1 Hz clock. This also consists of some transistors and integrated circuits, providing resources for conducting the experiment. Then we have the dual trace oscilloscope. In general, an oscilloscope is a device used to visualize and analyze electrical signals generated from the circuits. The dual trace oscilloscope included in this setup allows for the simultaneous display and comparison of two different signals, facilitating detailed analysis of waveforms. Then we have the digital multimeter, which is used for measuring electrical quantities such as voltage obtained from the experimental's trainer kit. Then we have the multiplier. The purpose of this multiplier is to amplify the results obtained from the pulses generated using the slotted disk. So as the rotating disk generates 15 pulses, the multiplier multiplies it by 4 and provides us data of 60 pulses. Then we have the wave shaper. So a wave shaper is a circuit that alters the shape of an input waveform. It can be employed to modify signals characteristics such as amplitude, frequency, or waveform shape. Then we have a timer. This timer is used to utilize the control of timing of operations within the experimental setup. It enables precise timing intervals or delays, contributing to the synchronization as well as coordination while measuring the rotation per minute of the rotating wheel or the slotted disk. Yeah. Then we have the variable DC power supply. This power supply unit offers adjustable output voltage levels, allowing us to provide variable DC power to different components and circuits as needed. So it will provide us with different voltages on the DC motor, and hence we can change the speed of the DC motor. Then at last we have the electronic counter with 1 Hz clock. This electronic counter is utilized to tally the number of pulses generated by the slotted disk, which are also multiplied in the multiplier. And this 1 Hz clock signal generated by the counter provides as a reference frequency, aiding in the measurement and analysis of the rotational speed. Now moving on to the experimental setup described in the video.
I will be explaining the circuitry of this experiment. So we have a dual trace oscilloscope which we use to measure frequency and see the waveforms. We have a multimeter which we use to measure voltage around the terminals of our motor. And we have a speed measurement trainer which has a 5-volt power supply, a wave shaper which converts analog signal into pulses, and a multiplier, 1 Hz clock which is connected to the counter which measures the RPM of our motor.
Now we'll be discussing about the instrumentation setup here. So this instrument consists of a rotating wheel with 15 spikes. It also contains the optical sensor here. This is the light emitting nerve, and this is the optical sensor, which basically detects any kind of electron or photon that is coming from this light emitting nerve. And it also contains the DC motor connected with the circuitry here. So what usually happens is a voltage is provided from the circuit to the DC motor, and which turns this rotating wheel here. So whenever there is an obstruction between the optical sensor and the light emitting diode, current is not generated, and which is detected by the instrument, the experimental setup.
First we increase the voltage of the motor and measure the voltage across the terminal of motor using digital multimeter. Now we will insert the pin after wave shaper and measure our frequency using cathode ray oscilloscope. Then insert the pin after 4x multiplier, measure the frequency again, and we will also note the RPM using display on the trainer kit. For the second set of reading, we need a stopwatch, and we increase number of pulses and find the number of pulses per second. So after taking several readings, we get these two observation tables. We calculate speed using diameter of disk. As we can observe, the graph plotted between counter reading from optocoupler in RPM and frequency reading from cathode ray oscilloscope have a linear relationship, indicating that optocoupler are indeed efficient in measuring rotational speed. Precautions: be extremely careful of rotating slotted disk at higher speed, it can cause damage. Do not provide high voltage to the motor, as readings might fluctuate more and motor becomes unstable. Average out the fluctuations present while taking frequency measurement from the oscilloscope.